a y acceleration, ay, of negative 10 meters per second squared. It's known. You just may not be told that in the problem. Okay, next, sometimes we have two things, and there's a classic problem where you have a car that drives by a police officer. The police officer starts at rest, the car is moving at a constant velocity, the police officer accelerates at a constant rate, and the question is something like, how far will the car have gone before the officer catches up? Or how much time will go by? And those are two separate problems because the police officer has their acceleration and the driver has their acceleration. It's two different constant accelerations. One is zero, one is non-zero. So you have to solve those separately. You're not going to have to worry about this right away, but you will eventually. Yeah?
You want us to use 10 meters per second squared?
Doesn't matter. Yeah, you can use whichever one you want. The actual value is closer to 9.8. In practice, it's not going to make any difference for the work that we're doing. So usually people just use 10. This is a more general case of what I just said. When you have two objects, it is two different accelerations, which means two different problems. If we have one problem, one object, but its acceleration changes, that's two problems as well. Anytime we have different constant accelerations, we have to solve everything separately. I talked about this already. This gets weird. When we talk about initial and final values, you'll see an example of this shortly. Basically, what can happen is that we want to say the initial velocity is some number and it's fixed and we all know what it is and we all know when it happened. But the truth is, the kinematic equations apply over different time periods. So you might have one time period that you're thinking about over here with its own initial and final velocity, and then some time goes by and later on we're interested again. We have a different initial and final velocity for a different time period. Initial velocity is not something where there's just one. Initial velocity is relative to a specific object over a specific time period. So that'll take some getting used to. And then the last thing, and I did mention this already, but when we have time in our equations, it's always delta t, the amount of time that goes by. So a lot of times we set up our graphs or our equations and we say, well, whenever we first are interested in something, that's time 0. And then 6 seconds goes by. So our final time is 6. Our initial time is 0. 6 minus 0 is 6. The change in time is equal mathematically to the value of the final time. That's not always true though. Because if we're then interested in a problem later involving the same object, it does something kind of weird, and then 10 seconds into our problem, it starts accelerating at a constant rate, and it does that until 16 seconds. Then we're going from 10 to 16. So our final time is 16, but our change in time is 6, and that's what matters. Okay? So these are not things you need to write down. These are things that will trip some of you up at various points, and what you'll need to do is just come back to this slide, and unfortunately there's other things too. These are some of the typical tricks that you'll see. There's more. All right, so the next thing that I want to do is solve a problem for you, a sample problem, but let's take a break first. So let's take 5, and then at 10:50 will you come back and we'll work through this problem together, and then you'll be able to do some work on your own.